So almost for the rest of the day now, we're going to be looking at spectrograms. First, I just thought I'd start off by going over some of the terminology we're going to be using throughout the afternoon, because I'll be using it a lot. So I would like everyone to kind of get used to some of those terms. I think I also did send out a sheet of definitions that hopefully you have, so you can use that as a quick guide throughout the afternoon. So we spoke about spectrograms earlier. So basically a spectrogram is just an image that displays sound waves. You may also hear people refer to them as sonograms. It's basically the same thing as sonogram, is just used more in terms of health research, but essentially it's the same thing. So you can see this is our spectrogram, and we can see the sound waves displayed in this image. So within the spectrogram, we have a call or a pulse, which is each separate line of sound, and it usually sweeps from high to low frequency. And each of these calls or pulses represents a single echolocation call of a bat. So you can see I have a call circled in blue here, and there are multiple calls in this spectrogram, which make up the call sequence. So the sequence is the series of calls or pulses. So everything in the red would be the sequence, and it's made up of multiple calls or pulses. So we also need to define what a bat pass is. So a bat pass is the unit of measurement that we often use when calculating species magnitude of activity during our stationary point surveys or our species relative abundance estimates during our mobile transects. So any bat defines a bat pass as a sequence of calls pulses that are separated by at least 2 seconds. You don't really have to worry about that too much because you will see in the detector settings, I think Yordi has that in a video online, but when we set the detector, we set the detector trigger window to 2 seconds, and that should ensure that each separate recorded file constitutes a separate bat pass under any bat's definition. But we do have some other conditions that should be considered when manually identifying spectrograms and designating files as a bat pass. So sometimes files are poor quality depending on the recording conditions, like if you're in high clutter habitat or if you're recording during a mobile transect and there's a lot of noise. And even though the detector actually makes a file, the file quality may not be sufficient to be confident in identifying the calls as those of a bat. So in order for a file to be designated as a bat pass, it needs to have at least 3 discernible bat calls or pulses in 0 cross, not full spectrum. And I will define those 2 terms for you later. But basically looking here, 0 cross would be the white and purple dots, and full spectrum here would be just the green lines that you see. So you can see here in this file, we have 3 pulses that show up in 0 cross. So we would call this a bat pass. In the middle image, we only have 2 pulses in 0 cross. So we wouldn't be able to call that a bat pass, even though it is likely a bat. To be conservative, we would call that file noise. And then in the last image, we actually have 4 calls or pulses, but they're all only in full spectrum. They're not in 0 cross. And so we would not designate that as a bat pass. So something else you need to consider is that sometimes more than one bat is recorded in a single file. And that's why we can't just say, oh, we have this number of files, so we have this number of bat passes. There may be identifiably more than one bat of a single species or multiple bats of multiple species. So in this case here, you can see in the red, that's one bat of a certain species, and in blue, we actually have a second species or species grouping here. So in this case, we have 2 sequences and 2 bat passes within one audio file. Okay. So now we're going to zoom in and actually look at each call or pulse. So the call body is the part of the call with the lowest slope, the flattest part of the call after the knee. So you can see that's highlighted in red. The Kaleidoscope software, I show this in the video on using the Kaleidoscope software, but you actually have an option with the 0 cross where you can highlight the call body in purple. So you'll see here all of the call bodies will be in purple. I like having that setting on so I can actually visualize it. You also have the knee and the elbow, or the elbow, I should say, either or. I usually refer to it as the knee, but this is the bend in the call that is sometimes present, and it can either be indistinct, so more of a smooth, rounded appearance, or it can be distinct, so it can look more sharp or angular. And that's just, I'm pointing to the knee with the blue arrow here. You also can have a tail or a toe. Again, I usually refer to it as a toe, but it's the hook on the end of the call that is sometimes present after the call body, and it can either be upturned or downturned. So here it's downturned, it's circled in yellow, and then on the right, an upturned toe is shown in red and a downturned toe is shown in blue. So those are kind of the main parts of the call or pulse that you should be familiar with for species ID purposes. So looking at different kinds of frequencies, we'll mainly be referring to the characteristic frequency, which is also called the FC. So because characteristic frequency is a lot to say, I'll probably just call it FC later today. But it's basically the average frequency of the call body. So it will take the average frequency of these purple call bodies if you're looking at the whole sequence, and that gives you your FC or your characteristic frequency. In a few cases, we also need to know your minimum frequency and maximum frequency. So your maximum frequency is just your uppermost part of the call. So you can see here it's highlighted in yellow. We also call that Fmax. You might not always actually see the Fmax in a pulse because the higher frequency sound waves cannot travel as far in the air. So you often lose the higher part of the call first. So you can see like in this first pulse, maybe it does actually go up closer to 65 kilohertz, but we've lost those upper frequencies because the sound does not travel as far. So your minimum frequency or your Fmin, which I have highlighted in blue here, is the lowest frequency of the call. And when we're talking about frequencies with bad echolocation calls, our units are typically kilohertz. Okay. We also need to know a little bit about slope. I'm not going to take you back to high school math, but basically we just need to know what the call body slope is. We also call that SC. So again, that's the slope of the call body. So that purple part of the call here. It is also considered the characteristic slope of the call. And we measure the slope in OPS, which is octaves per second. So basically, if the call is flat, like you see up here, you're going to have a lower slope. So we have a slope here of 9.77 OPS. So that's fairly low. If you have a high slope, your call will look quite steep. And here the slope would be above 500 OPS. So we know that that's quite a high slope. You shouldn't be seeing a negative slope with bat calls. If you see a negative slope, it's either because you have fractionated poor quality calls where the software is just struggling and estimating the slope, or you're potentially looking at noise or maybe bird calls or another animal. So if you're getting negative slopes, that's your first clue that something's wrong. And you can calculate these easily using the software. And again, that's all in that instructional video that we have on YouTube. I think these are the last two terms that might be useful to know. So on the left, we have time between calls, or TBC. So this is just the length of time between each pulse. And it's typically measured in milliseconds. On the right, we have duration, which is called dur for short. And this is the length of time of the pulse in milliseconds. So TBC is measuring the time between each pulse, and your duration is measuring the time it takes to emit a single pulse. Okay, were all of those terms clear? Yeah, great. Okay, so now I'm going to get into full spectrum and zero cross analysis in a little more detail. It is a little technical, but I don't think it will be too bad. So this image here just shows, using the Kaleidoscope software, how you turn on your full spectrum and zero cross, which Matt, I think, mentioned earlier. Again, that's all in the instructional video, but I just think it is important to define these terms. So your acoustic data basically can be recorded and read in both full spectrum or zero crossing formats. Some detector types can be set to record in either format. So if you saw earlier, Yordi was talking about the SM4 bat FS. So the FS on the end of that stands for full spectrum. So that detector actually does record in full spectrum. So just to note that your full spectrum format can always be converted into zero crossing format afterwards. So we can take the data from that detector and convert it to zero crossing files afterwards, but you can't do it the other way around. So if you only record zero cross files, you cannot convert those at a later date to full spectrum files. So we do recommend that all of the data are recorded and stored in full spectrum and then converted with Kaleidoscope to full spectrum for convenience of data analysis. SD memory cards with appropriate data storing capacity should be used with acoustic detectors. And if you're doing just NA-BAT monitoring, so that 4 to 7 night monitoring window, if you have an SD card with at least 32 gigabytes, that's typically sufficient. But obviously, if you're monitoring for a longer period of time, you would have to consider that and consider changing the SD cards throughout the monitoring period. So full spectrum recording means the full spectral composition of sound is recorded. So basically it's just recording the full aspect of the sound, and it results in an audio file format that captures the highest resolution of audio file for further analysis. So this permits a higher level of detail to be read from these files, but it also results in files of larger size. So that makes sense. You're recording more information, so the files are larger in size. The full spectrum files are where you'll often see feeding buzzes, harmonics, which we'll look at both of those later. And it will also allow you to capture calls emitted by multiple bats at the exact same time. So you will see files with full spectrum where you have more than one bat within one file. Full spectrum audio files recorded with the detector will have a .wav or .wac file extension. So you can see here looking at these two images, the one on the top is full spectrum and the one on the bottom is zero crossing. This is the same file, but you can see the zero crossing does not pick up all of the pulses that the full spectrum does. The full spectrum is recording more information and more details, which you're losing some of that information in the zero cross format, which I'm just highlighting here. So the zero cross recording will result in an audio file format that only captures the frequency of the sound recorded at any time with the highest amplitude. So it's not really the same as volume, but you can kind of think of it as the loudest sound, but it's the highest in amplitude. So that's what I was saying to Matt earlier, that the zero cross files are only going to be recording the sound with the highest amplitude at that given time. So the fundamental nature of zero crossing is to analyze high frequency sound that is louder than the ambient noise. So it will pick up the loudest sound. So if the bat going by has higher amplitude than like the insects and the rain and the grass blowing, it will pick up the bat. But if some of those ambient noises, like if the wind blowing is louder than the bat, if it's higher in amplitude, then the zero cross format will not pick up the bat flying by. So this method of data collection results in file sizes that are only a fraction of full spectrum files, but there is less detail retained in the stored file. The zero cross audio files typically will not capture feeding buzzes, and they do not contain harmonics. And they often also won't have calls of two bats, because again, it's only recording the loudest or the highest amplitude calls. So if you have two bats and one's a little closer to the mic, it's going to record that bat. But if you have a bat of lower amplitude that's a little farther from the mic in the background, the zero cross will not pick up that bat. The zero cross audio files have the .zc file extension. And though Kaleidoscope allows the viewing of full spectrum data, its underpinning analysis is based entirely on zero cross analysis. For all of its calculations and measurements, Kaleidoscope will only use the frequencies that are louder than the underlying noise. So basically, when we're looking at files for ID purposes, I would always recommend looking at the file in full spectrum to get the full picture. But when we're looking at pulses and we're looking to ID to species, we are using the zero cross format to ID to species for consistency. And when you're using the calculations that Kaleidoscope produces, like the slope, the SC, Kaleidoscope is only using the zero cross recording to make those calculations. Okay. So yeah, again, you can see here. So the full spectrum file has recorded harmonics up above, which I'll get into later, but you can see that the zero cross file does not pick up that aspect. Okay, was that clear about zero cross versus full spectrum? Yeah. So we'll basically be looking at both throughout the afternoon, but we will be relying on zero cross for ID and for designating files as a BAT pass, if that makes sense. Okay. So I just want to show you here as well, because I will, in later images today, I will be showing you the spectrogram in both normal and compressed time. So I just want to be clear about what you're actually seeing. So the normal time view is the call sequence displayed in real time. So you can see along the bottom here, the x-axis is measured in seconds. The compressed time view, so this is the same file, but in compressed time view, it will display the call sequence with your TBC, or your time between calls removed. So see how here the spacing is wider apart at the beginning, and then it becomes closer together, and then a little farther apart. So that's actually how the BAT is echolocating. In the compressed time, you can see that each pulse is separated by the same amount of time, and that's artificial because it's actually removing the time between calls. So it is important to look at the sequence in normal time to get full understanding of what is happening in the spectrogram. So this is usually where you can tell if there's more than one BAT based on the pattern. So that can be really helpful. But then you'll want to look at the file in compressed time when you're IDing to species, because it's a little closer and gives you more detail. So you can actually look at each pulse and look for some of those call features for the particular species. If we're feeling okay, I'd like to go over a few questions together. And again, even if you're confused, I would recommend you answer indicating your confusion so I can better explain things, because if you have a question, I can guarantee someone else likely has the same question. Okay, so we'll go over these and then you can just answer by unmuting or putting your answer in the chat. And of course, you can always ask questions. So would this file be considered a BAT pass? Why or why not?
Yeah, there's a couple in the chat. Yes, 3 passes and 0 cross. Yeah.
Okay, great. Yeah. So awesome. You all nailed it. That's fantastic. Maybe you've done this before, but if you haven't, that's really good too. So yeah, we can see here there's 1, 2, 3 pulses with this white and purple, so our zero cross. And we require 3 pulses and 0 cross to have a BAT pass, so that fits. We also have a pulse over here that's only in full spectrum, so we would ignore that one. And then this is noise, these lines here. So there is a little bit of variation here depending on the observer. And this is why acoustic ID is not an exact science, but it does rely on the person actually IDing the files. So I could look at this and I say, yeah, 3 pulses and 0 cross, BAT pass. Yordi could look at this and say, there's 3 pulses and 0 cross. The first one and the last one are pretty good quality. That middle one is like a little bit iffy. We definitely lost the top part of that pulse because there are always frequencies above the purple part, like the call body. And so he might decide that this middle pulse isn't of sufficient quality to be considered a full pulse, in which case there'd only be 2 pulses and he might screen this as noise. So here I would either accept this as a BAT pass, or it could be noise as well if you felt like these weren't good enough quality pulses. Does that make sense? I'm assuming it does. Okay.
Yes.
So for this one, I want you to match the call, so the letter, to its name, which is represented by a number. So match the part of the call to the name, essentially. So the letter to the number. Is that clear? I'm always really bad at explaining it, but I think It's just like a matching exercise.
I think it's clear because answers are coming in. So I'll translate. I'm seeing A is knee, B is call body, C is tail toe. Someone else, yeah, several other people saying the same thing.
Okay.
Call body is B, A is knee, C is tail,
Okay.
B is body. Yes.
Okay. I think everyone has put the right answer. So I don't think there's any confusion there. But yeah, the B, and this is always our little trick today, the call body will always be in purple. So B is the call body, which is 1. Here we do have a knee or an elbow as at A, so number 2. I will be using the term knee probably for the rest of the day, but you can also call it an elbow if you want. And then C is our tail or our toe. Again, I use the term toe, but you could also call this a tail. So C is 3. Good. Here we go, toe. Does this call have a toe? If yes, is it upturned or downturned?
Downturned 3 times, 4 times, 5 times. Yeah.
Is it all, do we always have like the exact same people answering? Do you ever check for that?
Well, we get quite a number of answers, so no, I'm not actively checking for that.
Okay. Yeah, you're right. We do have a toe. It's this white part after the call body, and it is pointing down. So it is downturned. Yes. Good. Okay. Which letter represents the frequencies used to calculate the FC? What does FC stand for, and what unit is FC measured with? A lot of questions here. If you only can answer one of them, that's fine.
People are saying B.
Okay. So for the first part of the question, yes, B represents the frequencies used to calculate the FC. So it would be the average frequency of the call body, which is in purple. So B. So yeah, good. You use the average frequencies of the call body to calculate the FC. What does FC stand for?
Characteristic frequency.
Awesome. Yeah, characteristic frequency. Perfect. And then what unit is FC measured with or in? Oh,
Kilohertz.
kilohertz. Great. Awesome. Bonus question. So if we're talking about frequencies, what do A and C represent in terms of frequencies?
Max and min.
Yeah, great. So A is your Fmax and C is your Fmin. Perfect. Nailed it. Okay.
Ooh,
Another
perfect score.
similar, what?
Perfect score.
Another similar question. So what does SC stand for? What units is SC measured with? And does this image have a low or a high SC?
I'm seeing call sequence, call body slope, another call body slope, low.
Mm-hmm. Good. Yeah, so SC stands for SC stands for call body slope. This is a bit confusing because FC is characteristic frequency, so I would think this means characteristic slope, which it technically is. It is the characteristic slope, but the term is actually call body slope. No one put the units, so we still need to know the units. I'm not going to answer that, but we do think this has a low slope.
Kilohertz per millisecond and OPS are the answers I'm seeing.
Sure. Yeah, OPS. So, right. It's measured in octaves per second, which is technically kilohertz. I guess it's per second, not millisecond, but you could just always calculate it to milliseconds. So that's
you could do it in kilohertz per minute as well, really.
Yeah, you just need to convert it. So yeah, all of those answers are right. So you don't really need to remember what OPS stands for, but throughout the day you'll be seeing OPS. So I want you to know when you see a number then OPS, that means your SC essentially. So octaves per second. And then we had one person answer that they think this is, I think, a low slope. So when you're actually using the software, you can calculate it, which I did here. The slope is 10.58, which is low, but you can just eyeball this and see that the pulses look pretty flat, horizontal, and so it would have a low slope.